Okay, so question 18 of the exam 1 review. Moving on to buoyancy. Sorry, the figures are slightly dark here. So what we have is block A. Block A is placed in a container of honey, and 25% of the block's volume is submerged. So that's sort of what the picture this line is representing. So there's only 25% of the block submerged, 75% above the surface of the honey. And block B is placed in an unknown fluid. We know that block B is 3 times as dense as block A. Sorry, but sort of put the A over here. And when placed in the unknown fluid, 60% of its volume, that's block B, is submerged, so below the surface. So we got 40% above for B, 60% below. And we're looking for the density of the unknown fluid. So it's sort of tough, sort of ratio type question. Sort of linking similar quantities, so like A and B are linked to their density. We know the density of honey, so sort of we figure some quantities out for A and then sort of transfer them in for block B. So both blocks are floating. So in should you see this? So for flotation, the key condition for flotation is that the magnitude of the buoyant force equals the magnitude of the weight. That's what basically keeps the block at rest. So the weight force is being balanced out by the upward buoyant force. So the buoyant force though is given as the rho of the fluid times G times the volume displaced. So I'll do this for block A. So that's rho of honey. I'll just use H for honey, that's okay. G times the volume displaced equals the weight of block A, which is the mass of A times G. But I can write the mass of A as the rho of A times the volume of A times G. So mass can be written as rho times volume. So what we see here is that I'm going to cancel out that G there with this G here. So I've got rho honey. Now what we're told is that the volume displaced is 25% of block A's volume. So the displaced volume is 0.25 of the volume of A, and that's equal to rho A VA. So I can get rid of those volumes. So I should be able now to describe that the density of A is only 25% the density of honey. And this goes true for all problems, in a sense. The thing about the submerged volume. So if an object is 60% of the density of the fluid, it will submerge 60% of its volume, assuming it's not non-porous, and so on. Okay, so now we have a connection between the density of A and the density of honey, which is a known quantity. So what we want to do is apply a similar analysis for block B. So we know that for block B, the density of the unknown, I'll use U for unknown. So, well, let me just start from the start here. So I know that F of the buoyancy of B is equal to the weight of B. So the buoyant force in block B is the density of the unknown fluid, use U, times G times the volume displaced, equals, again, the weight of block B, which is the rho of B times the volume of B times G. And using the same principle as up above. So we can go out and cancel out those G's. And the volume displaced in example B is 60% of the volume of B. So I can get rho U times 0.6 the volume of B equals rho B BB. And now I can cancel out the BB's. So the rho of the unknown is PB, rho of the block B divided by 0.6. So rho of the unknown quantity is rho B divided by 0.6. And now we're sort of almost the final steps, because we can relate that the rho B is 3 times the density of block A. And so I can replace this rho B with 3 rho A. And and we know rho A in terms of the density of honey. So that's 3 times 0.25 times the rho of honey divided by 0.6. So if you substitute in the 1.4 kgs per litre for the density of honey in here, all their numbers are constants, or like known quantities. So you should end up at 1.75 kgs per litre. So choice C being the correct answer. Okay, that's clear.